So welcome very much to the EcoExplore Intro to GLMs. I'm Jez Smith. My background is in ecology, specifically pied flycatchers and migrant songbirds. Today, though, we're going to be looking at understanding how general linear models, so explaining y variables with x variables, both continuous and categorical, how they work in R. And we're specifically going to be looking at weather data today. So trying to understand how temperature changes between months and across years. As I say, my background is sort of in stats, but also in the ecological side of things. So hopefully this will be very much a kind of someone who uses the data and uses the software and uses the techniques rather than sort of a pure statistician providing the information. So what is a general linear model? Well, what it is it's a collection of sort of smaller, less powerful tests. So for example, everyone will probably be familiar with t-tests when you're trying to compare the mean of one group with the mean of one other. And then obviously many people will be used to analysis of variance or ANOVAs, where you're trying to compare multiple groups, more than two groups of continuous data. We've also got regression and correlation, and the fact that two continuous variables can be sort of associated with one another. And then actually, if you bring in more continuous variables, then you can have multiple regression. But the strength of GLMs, specifically general linear models that I'm going to be talking about today, is the idea that you can have continuous and categorical variables in the same model. So you can control statistically for one variable whilst looking at the effect of a second variable. And this is a really sort of important element within modeling. Where this would go is looking at generalized linear modeling. So we'll come on to the idea of error distributions and sort of what data they represent, and the idea that you can look at non-normal data. So when you have the unexplained variation at the end of your model, they're the residuals, and the idea that you can have some specific structures such as count data, which will never be normal despite what you try and do to them. And that's where generalized linear models come in, but they still look at straight line relationships between your x variable, or x variables, and your y variable. Sometimes, though, you have variables that you don't want to try and explain, but for methodological reasons or others, you may need to incorporate those into your model. And that's where generalized linear mixed modeling comes in. And beyond that, you can have non-linear relationships, and we're moving into general additive models and general additive mixed models. I won't go into any of those this afternoon and this evening, but just to say that they exist. And one of the elements that we do at EcoExplore is we teach courses that cover all of these topics. So if you're interested in that, do drop me a line afterwards. We have a course coming up in May. So it's a 5-day course from the 16th to the 20th. And if those sorts of things are something that you're needing assistance with or needing to learn, then as I say, drop me a line or look at any of the adverts that are out at the moment. So how do general linear models actually work? Well, if you're scared about the Greek, don't worry. This is the same equation is going to come up twice, one in a couple of slides time, and this one, but that's it. There's no more kind of Greek, there's no more mathematic notation through the rest of the session. But what those Greek letters, the betas, actually represent is the relationship between the x and the y variable. And every variable that you have, every x variable, has its own relationship with the y variable. So these are called the beta coefficients. So the y variable you have, in this case it's going to be minimum temperature, has a relationship with each of the x variables. The beta xi at the end just says that this could be an infinite number of possible variables. And the final bit saying the error is all about sort of the model structure and what the distribution of the y variable is. We today are going to be looking at models where we have normal distribution, a normal error, or otherwise known as a Gaussian error. So all of the tests that we're going to be looking at are going to test the relationship between the dependent variable and how that can be explained by the independent variables, the x's. As I said earlier, we have both continuous and categorical variables in this. If we just had categorical, then we'd be looking at analysis of variance. If we just had continuous, we'd be looking at multiple linear regression. So we need to have both in order for this to be a GLM. There are also some assumptions. As with all modeling, whenever we have a model, we have some assumptions that go with it. The assumptions that go with the GLM are the same as those that go with analysis of variance. Namely, we have a normal distribution of residuals. So that doesn't mean that the data have to be normal going in. It means that the leftover variation in data needs to have a normal structure. So a few small ones at either side, with the main number of observations being in the middle. And the equality of variance as well, also known as homoscedasticity, and the idea being that across the range of data, we have equal variance. So therefore, we have the same number of data points either side of the zero line, and that is the same case both at the lower end of your x variable and at the upper end. And we'll see those in graphical form in just a second. And the third of our assumptions that we need to meet is that there is no excessively influential observations. Now, if we were measuring something such as temperature, and most of ours were in the range of 0 degrees to 30 degrees, and then we found out that there was one that was 100 degrees, the model would try and fit that into the model structure as best as possible. And so what it would do is it would pull the pattern into a position that is not appropriate and not applicable. So we need to make sure that when we're running our models, that none of these observations are excessively influential. It can also happen if we aren't explaining some of that variable, and we'll come on to that a little later on. So what are we going to look at today? We're going to be looking at Welsh weather, because I'm based in Wales in the UK, and so this is a common topic, as anyone who's met me or anyone who's met anyone from sort of Wales, the UK, etc. Will know. But what are we trying to do with it today? Well, we're trying to explain the variation in weather across the months and across years as well. So we're going to be looking at month as a categorical term. So how does it compare from one month to the next? And how does it compare across a range of years that we have? So specifically, the research questions are, is minimum temperature in this context associated with month? And at the same time, and this is the importance of the GLM, is the temperature associated with year? And these are what we'll call main effects. And we'll come on to other types of effects later on. So each effect is examined simultaneously whilst controlling statistically for the other effect. And this is something that ANOVA and multiple linear regression doesn't do. And so that's really important, that controlling for one variable whilst looking at the relationship between the y variable and another variable is what this GLM does so well. Okay, so what we're going to do is I'm going to switch between our studio, where I'll be running the session, and PowerPoint when I'm sort of talking about what we're doing or what we've done. So what I'll do is I'll talk us through the next slide, building the model, and then I'll actually go into R and I'll start implementing it. So what we need to do is we need to actually start creating the data. So we've got an object I'm going to call model 1, and this is going to use the function GLM. So this is a very powerful, very general function, the GLM function. and I'm going to be explaining minimum temperature. And I'll show you the data in a second. And then what I'm going to do is I'm going to relate that, so using a tilde, with month and year. The family equals Gaussian is what I was saying before. We are expecting a normal distribution of residuals, and we'll see why that might be in a second. And we're expecting a straight line relationship between the x variables and the y variable. And so that's why we have this link equals identity. That means a straight line relationship between the y and the x variables. We also want to make sure that our data frame is symmetrical. So any missing values that we have, we just want to remove that row so that we end up with a nice structured data set so that we can compare and we can sort of plot predictions in the future. So we're going to exclude the NAs. And then we're going to specify that the data come from what I'm going to call dframe1, which is the object containing all of our weather data. So if I move into our studio, I can then show you our model. Two seconds, it managed to have closed itself down, which is unhelpful, should we say. Okay, so hopefully now you can see my RStudio. And these are the data that I put a link in on the website from, and also on email if that's where people requested them. So I have set up a project for this session this evening. So that's just to say that I have intro to GLM here. So my working directory is already set. I'm sure many of you are very familiar with R, but for those of you sort of who aren't, I tend to make sure that the environment on the right-hand side is empty before I start, just so that I'm not accidentally running historic data. So if that isn't the case, I use the rm list equals ls function just to remove anything that's there. As I say, I've already set my working directory. So what you have, which is unhashtagged, is the path to my folder, but I already have that set. So let's move straight into reading the data. So it's the weather CSV file that's provided with the script file, and I'm just going to read this in as dframe1. The other thing to say, as you'll see as we go through, this script isn't written sort of in a tidy format. So these aren't tibbles, for those of you who are familiar with that. And we only use a little bit of sort of the tidyverse later on when we're looking at EM means. So all of the plotting is done in base R. This isn't for any reason other than we often find that people learning it for the first time find this more sort of intuitive once you've started running with base R, but this is just how it's been done. But there's no issue, obviously, with sort of ggplot and all the rest of it. So if we look at the whole of our data frame, which we can do by just running the name, you can see that we've got years running from 1977. We've got months coded with the number, and then we've got maximum temperature, minimum temperature, the number of frost days, the quantity of rain in millimeters, and the number of hours of sunshine in that month. So it's a nice kind of holistic view of some of the weather variables. If we only wanted to have a look at the top 6 rows, then we can just use the head command, and that provides us those 6 rows. It's just very useful if you want to have a quick snapshot of your data, but you don't want to have to plot the whole thing, and you don't have it in a shorter version, such as a tibble. We can also have a look at all of the variables as a summary, and that just means it's easier as well to kind of check the min and max values, and just make sure that there aren't any big outliers that we can see straight from the off. For example, in here, we had 27 frost days that occurred in one time point, but most of the number of frost days was sort of 5 or below. So just to sort of say that if you're looking at the number of frost days, this is something to be aware that there are sort of extremes in certain data sets. And the other thing that we find is very useful is just making sure that you know the names and how they're specified in the data set. So if there's any spaces, they'll be filled in with full stops or periods. If you have any sort of underscores or brackets or things like that, just make sure you know how R is reading them. So you guys aren't familiar with this data set per se. So one of the quick ways to do it is just use the plot command to have a look at all of the variables in turn. This is a very quick scatter plot whereby you can see that the relationship both with each variable on the X and on the Y is shown, and how they vary between. So here we can see that minimum temperature on the X in this case and maximum temperature on the Y have a very strong correlation. So we might want to use one or other of these in a model. We might not want to use both because of covariance. And particularly, you'll see sort of at other points, variance inflation factors mentioned. We can also have a look to see how minimum temperature is changing through the months in this continuous manner, and how the minimum temperature changes through the year. But this is a much harder thing to see, so we might want to look at some of those terms individually. So I've been talking about how today is about general linear models, so not generalized. So we're expecting not the data that goes in to be normally distributed, although that is generally the case as well. So if we have a look at our Y variable, in this particular case is minimum temperature, we don't have a normal distribution, but what we do have is we have a true sort of distribution in the sense of it goes below 0. So it's not bounded, which a gamma distribution would be. That would be sort of continuous data but bounded at 0. Here we have continuous data because although the temperature has been measured at a certain degree of precision, we could actually measure this with as many decimal places as we want. So it is truly continuous data. As I say, it's not bounded at 0, and it's not bounded above either. It could be, in theory, infinitely warm. So we have a normal distribution within the data, even though it has these two peaks, which is unsurprising, given that we have this bimodality in sort of spring and autumn. There's most of the time it's going to be a certain warmth, and the same later in the year. And we can do this for all of the potential variables that we have. And here we're doing maximum temperature. We can do it with rainfall, and we can do it with the sun, the amount of sun as well. All of these can be manipulated and made much, much prettier, but I won't go into that because obviously the idea of today is running GLMs rather than sort of making plots. But if we did want to have a look at specific X variables, so in this case we're looking at minimum temperature, and we wanted to see how that varies across the months, we can use the plot command, and we can just see as a continuous data set now with month, how minimum temperature varies between the months. But actually we're going to be using it as a categorical because we want to know what the mean difference is between certain months, and not what the spread of data points are within a month. So we're going to use the asFactor command to convert month into a categorical variable. So now if we do that, rather than getting the scatter plot, we end up with box plots. So we can already see that there are very clearly differences between the winter months and the summer months. So I'm talking sort of northern hemisphere, sort of Welsh weather, obviously. So summers are usually dry and warm. Winters are cold and wet. And what about temperature across the years? And this time we are going to be using year as a continuum. So we're just going to say from 1977, the start of our data set, through 2012, what's that? What's the change in temperature? And so here we are back at what we had in PowerPoint a few minutes ago. We've got our object, model 1, and we've got our main effects, GLM. So we've got minimum temperature being explained by year and month with all of our various other elements and arguments that we need within the model. So that's the simplest GLM you can have. It's got two variables, one categorical, one continuous. It's a Gaussian model, and it's a link identity. And so what we could then do is have a look at what the output of our data are. So if I just go back into PowerPoint, before we have a look at our model in depth, what we're going to do is we're going to make sure that the model assumptions that we made at the beginning are valid. So we have a normal distribution of residuals, we have an equality of variance, so therefore all the data points are spread evenly across the predictions, and that we have no unduly influential observations. We could do this manually. So you can see in the first part of the code up there, we can form these standardized residuals, and we can manually create those. And we can have a look at the histograms, and we can plot the standardized residuals against what we call the fitted values, which are the regular values produced by the model. So rather than having the irregular data which we've collected, here, as you can see, these values go from 140, and then at regular intervals, you're provided with those data. But as with the case frequently in R, someone has written a much more succinct piece of code than that for us, and so we can plot the standard model assumptions using just a simple plot command. And we'll see in a second how that works. So we use this plot model 1, and depending on whether your window is set up to have one graphic in it, or whether it's set up to have a 2 by 2, then we'll either have to cycle through all of the graphics, or we'll just be able to look at them in one go. So if we do that, we'll have a quick look at our summary before we do our model validation, because I think it's very useful, even at this point, to have a look just to see what's going on with the model, even though we don't know yet whether it's appropriate or not. One of the really important elements to make sure you're checking, which people tend to skip over when they're more familiar with it, is the very first part of the summary. So this call, this tells us what the model formula was that it's reporting on. So here, it's exactly what we asked for: minimum temperature, year and month, family equals Gaussian, etc., etc. Now, the reason this is really important is that, let's say you're running multiple models, and one of them you've been getting warnings for, other ones you've been getting sort of errors, and you don't know whether the model has actually run properly. But if you check the model call, then it will tell you exactly the model it's reporting on. So if you check that and you find that that's not the one you thought it was, then it's good to kind of go back and make sure that model has actually run accurately. So we've got the correct model here. We've only run one, the environment was empty, so entirely unsurprising, but it's still good. The deviance residuals, we will cover those graphically in a second, so don't worry about those values. And the really sort of interesting bit that we come to is this coefficients table. And for people who are new to GLMs, then this is going to be something that is absolutely crucial for you to kind of wrap your head around. And for those who have done GLMs before but want a bit of a refresher, then hopefully you recognize the table. But I will give you some pointers and some ideas of how to understand it. So the main thing to know is that continuous variables only appear with one line. So this is the slope you're looking at. So for every change of 1 unit in your x variable, your y is increasing or decreasing by the amount that is in the estimate column. So the estimate is either your slope or it's your mean. And so I'll go through those in a second. So here, if we're looking specifically at the relationship between year and minimum temperature, whilst controlling statistically for the effect of month. And that's the really important point. I know I've been emphasizing it, but you're looking at the relationship between year and minimum temperature whilst you have controlled for the effect of month, which, as we can see, is changing. So how to interpret this, this line here? So this is saying that the relationship between year and minimum temperature is for every increase in year, there is a 0.02 degree increase in minimum temperature. So scaled a different way, that means that every 10 years, there is a 0.2 degree increase, or as we're actually seeing in Wales at the moment, every 100 years, there is a 2 degree increase in temperature, which is kind of worrying because that's obviously what we're all talking about within climate change. And we're seeing that actually, even from these data at the moment, on a very simple GLM, we can see that the relationship between minimum temperature and year is that in 100 years, given this set of data, and if this relationship were to continue, and there are two big ifs, but if that were the case, then the minimum temperature in Wales in 100 years would be 2 degrees hotter than it is currently, and certainly 100 years from 1977, the start of the data set, it would be 2 degrees hotter from that. Now, that's the mean value, but very importantly, we also have variation around that. We can't just presume that the mean is accurate on its own, so we have the standard error. And that's presented to us in the next column, as you can see. So it's 0.02 degrees per year, plus or minus 0.006 degrees Celsius. We have the test statistic, so the t-value, which can be reported when you're looking at differences within a term. We'll come to that in a bit. But very importantly, we can also see that the p-value is less than 0.05, and so therefore there is a significant effect of year. And this increase of 0.02 degrees per year is statistically significant. Whether it's biologically so or not is a different question, but statistically, given the power of the data and the model that we have, this is a statistically significant effect. And in fact, because the p-value is lower than 0.001, we actually have a very highly significant, statistically significant effect. So that's how you interpret linear continuous terms. Every year increase, there is a 0.2 degree increase in the y variable. For the months though, we're talking about categorical variables. And so therefore this is a different interpretation. As you can see, all of the months, except for January, have been listed. Now, the reason behind this is that they are coded, that each of the months are coded 1 to 12. And in order for there to be the contrast between one month and the next, so a comparison, we need to be able to have a value as the reference level. So we are comparing all of these, the mean temperatures, mean minimum temperatures specifically in each month, with the mean minimum temperature in January. And so what we can see here is that month 2, so February, is very importantly not statistically significantly different from January. So although there is a value here on the estimate and standard error, there is no significant difference between February and January. However, when you compare all of the other months, specifically as a direct comparison, January to March, January to April, etc., there are statistically significant differences in mean temperature. And the only one of those months that isn't very highly statistically significant is December, which is, again, no surprise. We have a very cyclical weather format, and so therefore it's cold in December just before it becomes cold in January. And so this here is July, where we have a mean difference between July and January of 10.79 degrees, and that was controlling for the effective year. So that is the average of July's across the entire data set. And that is being compared to the average, to the mean January value across the entire data set. And that's then how we interpret the main effects of a GLM. And we'll come on to other bits in a second. So we're about to see whether the model is actually appropriate or not. However, before that, we can see how efficient the model is. So if we start putting lots and lots and lots of terms into our model, we're invariably going to be explaining more and more of the variation in our data. The problem is that as you're adding more and more terms, you also need the model to be penalized to make sure that sorry, 2 seconds. So we need to make sure that the model is penalized for the additional terms that you're adding into the model. And the way we do this is by using the Akaki information criterion, so the AIC. And the idea of this is that the lowest value is the best. So you can only compare equal model structures, so Gaussian identity and similar variables, and I'll go on to that a little bit more later. But effectively, what we want is the lowest AIC. That means that we have the most efficient model. So if we go on to actually checking the model residuals and the validation, we can use plot model 1. Now I've got my window set up for one plot at a time, as you can see, and so therefore in the console window I need to click into it to make sure the cursor is flashing, and then I will cycle through the next 4 plots. The first plot is looking at just residuals on the y-axis and your predicted values across the x-axis. So one of the things that we were talking about before is this homogeneity of variance. So what we want to see is all of these open circles. We want to see an equal spread across the x-axis and across the y-axis. If we have that, then we have this homogeneity. So what we don't want to be seeing is any kind of fanning out. So we don't want to find that at one side of the data, the residuals are very, very tightly packed, and then they fan out and they become very, very wide, because this means that we're not capturing the data very effectively at the right-hand side, and we're sort of over capturing the data at the left-hand side, and vice versa. Obviously, we don't want it fanning the other way. And the other thing that we don't want is any additional patterning. So I'm talking about kind of waves or any other clustering of points. If we have that, then there are probably other terms that we're missing in the model that we then need to try and understand, and maybe we need to incorporate those so that we can model that sort of patterning, and we can capture that variation, and therefore the residuals, the leftover variance that isn't being explained, is this band of data points. So as I say, we're looking for an equal spread across the data set. And specifically, as you can see here, you might be able to see a very fine red line going through 0. So this is exactly what we want. We want the mean to be 0, and we want the variance either side of the line not to be very great, which is roughly what we have here. There is some variation. So down in the sort of bottom left, you can see here, observation 400 is quite far away from the line, but generally the structure of the plot is that it's equal across the full spectrum. The second of our two is that we want to have a look at the normality of the residuals. So here, a perfectly normal distribution would be represented by the very fine dots in the background going off at an angle. So if our data were perfectly normal, all of the open circles would be along that dotted line. As it happens, you can see that the vast majority of them are, but specifically on the left-hand side, we have a sort of a larger tail, and very marginally on the top right-hand side, we have some deviation away as well. Certainly the right-hand side, I would have no qualms about, although it is deviating from the perfect distribution. Actually, the number of data points we have indicate that this isn't a problem at all. That's a tiny proportion of our data. And then on the left-hand side, that deviation is a little bit more concerning, because we have a greater number of points that are deviating further away. But again, generally, what this means is that we would be careful about interpolating at those ends, the far extremes, but the middle section of our data specifically is extremely well modeled. So it gives us a lot of confidence in the middle part of our data, and maybe just a bit more caution at the extremes of our data. The third plot that I'm showing here, the scale location, is very, very similar to the first one. The only difference is that these residuals now have been square rooted. So you'll notice that all of the values are positive. There's no negative values. So we have, again, this homogeneity across the full spectrum. And yes, that red line is slightly declining, but actually it's still, that banding is still fairly even. So it's not perfect, but it's very good. And unfortunately, much of the way to interpret these is slightly subjective. There are general bounds, and there are different ways of reporting these and different ways of viewing the residuals, but generally it's widely accepted that sort of the best model that you can come up with that doesn't violate those assumptions is a good model. And then the final model check that we're going to have is this idea of any excessively influential observations. So what's happening here is the model is looking to see whether any of the observations that we see in the model actually stretch or pull the model in a direction that makes it sort of warp, basically. What I'm going to do is I'm just going to show you what a hypothetical Cook's distance would look like and how we would know if there was a problem. And spoiler, there isn't here, because apart from in the legend down here with Cook's distance, we can't see a dotted line around the outside, which we'd be looking to see if we did have any issues. So here we've got all of these plots again shown, but this time we have the Cook's distance again here, this is the legend. This is just to see where the data points are. But if there was a problem, then what we would have is this line around the outside. And if there was a real problem, what we would see is it would cut into the corners here. And you would get a dashed line that said 0.5 or 1. And the idea being, if any of these data points are outside of those Cook's distance, then they really are excessively influential. And this is not something that we would want to be, this is not a model that we'd want to be reporting. And it's a model we'd want to go and check and find out why those errors were there. Is it that you have data that are incorrect, or is it that you have data that are just not being modeled correctly? And that can be for a host of reasons. So what we're then going to do is we're going to start having a look at, now that we know that the model is a good model, we want to see whether we can make it more efficient. And one of the ways of doing this, and there are multiple, is what we call stepwise deletion. Particularly, this is backwards stepwise deletion. So what we're doing, as it says on the screen, is we're going to start from a full model, so all the things we want to test, and then we're going to remove a singular term at a time, if appropriate, until we get to a point where all of the terms are significant, they're having a significant impact on the model. And when that is the case, we have our final model. This is particularly relevant if you're testing lots of hypotheses in a singular model, and you actually want to find out which are sort of the most important within that. It's really, really important that these are removed one at a time. So you can't remove multiple variables because you don't know how each of those were impacted by the removal of one other. So it is one at a time. We'll also see later on what happens when you have multiple variables, X variables, which are interacting with each other. So not just in the model, so not just year plus month, but an actual interaction between year and month, and then its relationship with temperature. And so you need to make sure that when you do interactions, you're removing what we call the highest order interaction first. So this is if you have a two-way interaction, so year and sort of year colon month, that needs to be removed before year or month. And you'll see that as we go on later on. And the way we do this is we do a drop one. So this is the backwards stepwise deletion. And because we're using a Gaussian model, so we're using sort of continuous data, we have the test equals F. If you were to use count data or binomial data, you'd have test equals chi. So that's sort of what's important in that part of the code. So if we do that, then we can see that if we use drop model 1, we can see down here in the console that we have each of our terms. Now notice that month now is as a singular line, and that is because we are looking at the variable and not the levels within a variable. So we're saying, is month important in explaining minimum temperature, rather than how does each month vary? Okay, it's a very important distinction between the coefficients table that we saw a minute ago and the model refinement table that we're seeing now. So the way this works, and the reason we looked at AICs earlier, is that we saw that the AIC was 1445.3. The way this table works is if you remove nothing, then the AIC is 1445. Excuse me. If you remove year, the AIC increases to 1458. And remember, we want the lowest value. That difference between 1445 and 1458 is a significant difference. So this stepwise deletion is showing that there is a significantly worse model if you remove year from it. And it's exactly the same with month, that if we removed month, then our AIC would jump to a massive 2,372. So this would make it a much, much worse model for removing month, and it makes it a much worse model removing year. So actually, at the moment, we have both of those terms that we have in the model needing to be in the model. So we don't actually need to do any stepwise deletion because the model is as refined as it can be. So let's just remind ourselves then with what the model output actually was, given the fact we've now validated the model by checking the model assumptions, and we validated the model by checking that it is the most efficient model that it can be. So here what we did is we looked at the impact of year and month, and we saw that there was a significant effect of year, and every year's increase, there is a 0.02 degree increase in minimum temperature, and then all of these months compared with January. Now, I didn't go through the intercept previously. The reason being that sometimes the intercept is very important, and what I mean by that is it has a true representation of the data. Sometimes, however, this sort of is nonsensical. What the intercept is, it is what is the y value when all of your x values are set to 0 or their base layer. What this means is, in this case, we are saying what would the minimum temperature be in the year 0 in January? And the answer is it would be minus 47 degrees centigrade. So it's not a wrong model because it gives us a value of minus 47 degrees. What it means is that the relationship between year and month with respect to temperature is accurate, but we shouldn't extrapolate these data back beyond 1977 because that pattern we can't predict. So in this case, it's slightly nonsensical. In other situations, it might be valid, but that's why kind of you don't sort of report it in the sense of you're not going to say the intercept was this. What you're going to say is the impact of month was this amount on temperature, or within the bounds of these years, the increase in temperature was this amount. So that's, as I say, why we sort of don't go into the intercept generally. So that's the summary, but we've also got the summary.lm, which is a very useful function because it provides an extra couple of elements that we don't usually have. And this is, the table is the same, but what we notice here now is that we have an adjusted R squared. So this is how much of the variation in your data, the whole data set, are you explaining? This is a proportion from 0 to 1. And so what we've got now is 0.89 explained, otherwise known as 89%. So 89% of the minimum temperature in Wales is explained purely by the year it was and the month it was. So that is a huge proportion of the variance being explained. And so therefore, this is actually a very important model. And even more so, you can then say the p-value was, because it was below 0.05, this is a statistically significant model as well. So there's a statistically significant amount of the variation in the data set is being explained by these variables. When you come to report the results, you also will always need to provide the test statistic, and in a GLM, that's the F statistic, where we've got the value, and then we've got the degrees of freedom, number of sort of levels of the variable, and the number of data points in the data set. So all of these are really important to be presenting, and I'll come on to that later. But what if we didn't want it to be compared with January? If we wanted it to be June, we can re-level the data set. all you need to do is make sure that inside the inverted commas is the level that you want to provide it. So if we re-level month, we then need to rerun the model. If we don't rerun the model, it hasn't calculated everything in comparison with June. It's kept everything in relation to January. So make sure you rerun the model. So if we rerun that and we ask for a summary, we can now see that the impact of year has been nothing, hasn't changed the model. It's just changed the numbers for months. And now we have month 1 being shown. So we've got month 1 and we've got all of the months except now we don't have month 6. So we're showing that that's the reference category. So once we've conducted the model refinement, which in this case we've already done, we would then go through and recheck the model assumptions. And hopefully by having a better model, a more efficient model, we would find that the model assumptions fit better. However, excuse me, if you found that actually the model fit was less good, then you might want to think about which other variables would be appropriate to place in your model to try and make sure that you're capturing all that variation. So the summary .lm specifically function that we've just used gives us a useful overview of the model. It gives us this overall significance of the model with the p-value, but it also gives us the proportion of variance being explained, which is this adjusted r², and it gives us the idea of this model efficiency. So as it says, it's good for comparing between models, provided they use the same data set and that you're not using widely different terms within it. So you couldn't remove year and month and put in day and another variable. You need to kind of have one model being compared with a very similar other model. As we saw, the impact of removing any of these terms is that you would end up with much worse models with much higher AICs, which we don't want. We then moved through and we had a look at the relationship between year, and we had another look at the relationship between months as well. And this gives us the pairwise comparison with January previously, now June, but it doesn't give us direct comparisons where you can keep each of the variables constant, but we'll see that in a second. And then the final thing that we would take from that is that we've got the number of observations, or the number of degrees of freedom specifically for the denominator and numerator. We've got the r², which we can see, and we've also got the F statistic, which I showed as well. It's just a question in the chat, which I will just have a look at. So there isn't a difference between summary.lm and summary.glm. It's just that summary.lm is sort of older in a sense. It's been more widely used. So yeah, that's how you do that. And then also a question of how do we obtain the regression equation? You can use those values that you're getting from the table to calculate it. Cool. 2 seconds. So I will answer sort of one more question, then we'll sort of carry on, because obviously this could we could go on for a long time, which would be great, but everyone's got to carry on with their days later on. So what does the test equals F do? I believe you mean sort of in the drop one, and what that does is it just means that the model, the function knows that you're using continuous data rather than sort of count data or binomial. It gives it an F distribution rather than a chi distribution, which is a different sort of mathematical background. Cool. So, as I say, what this does is it allows us to understand the relationship. The summary.lm and the summary allow us to look at between months, but it doesn't allow you to specify which year you're looking at when you're looking between months. And for this, we need contrasts. So here we can say, let's compare sort of situation A with situation B. And so what we can do here is we can say, right, we want to compare June, but specifically in the year 2000 with January in the year 2000. Whereas previously we were comparing June across all years, so the mean of June with the mean of January. And here we can do it much more formally. And we'll do this in just a second. And that's why you'll see that the values that you get, and this is now the contrast column here, is the mean difference between June and January in those years, and the standard error, but they are different from what you would have seen in the summary table earlier, because it is across just the year 2000 rather than across the whole time frame. So if we do that, what we'll see is that we can load the contrast library, which some people may not have, so apologies, I should have put the install packages function in there. But if you do have the contrast library, then you can load that. And what it does is it compares the first set of conditions with the second. So what I mean by that, and why I'm phrasing it that way around, is we are saying that June is 8.78 degrees warmer than January. If we put 1 and then 6, we'd have minus 8.78. So it matters which around the conditions are set. For those who don't have the contrast package and it doesn't work for, because for some people it doesn't, you can use other packages, particularly the EM means. And so I'm going to use, within the tidyverse, I'm going to use the EM means. And then what this allows me to do is it allows me to say, well, I want the pairwise comparison between all the months. So using the data from model 1, I can then have a look and say, right, between June and January, I had a difference of 8.78 degrees, and so on and so forth. And as you can see, the p-value is then provided to you to see whether these are significant differences between temperatures between the months. And it gives you the full spectrum. So it's a sort of very useful way of doing this post hoc set of tests. So that's great. But sort of what does it mean? And I must say that I'm very much a visual learner, and so I kind of like making plots of things. And I find that actually visualizing the patterning is a strong way of kind of showing up the data, as well as reporting it sort of in the text as well. So what I'm going to do is I'm going to create a basic plot where I'm just using the raw data of minimum temperature and year. And that's the raw data. And then if we want to look at the model parameters, we can look at summary. But actually, most importantly, what we need to do is we need to create predictions. So what this is going to allow us to do is we're going to initially color the original data, the raw data, and we're going to color any points from June in red. And we're going to then specifically model what the mean relationship is in June across the whole data set. And this is where the modeling part comes in. So we've got the raw data, and we could just plot a line, but whilst controlling statistically for the effect of month, then we can now have a look at this relationship. So the way we do that is we start by creating a grid of just a series of numbers between 1977 to 2012, increments of 1, so we get a point for every year, and where month equals 6. And then what we're going to do is we're going to use the predictions from the model, and we're going to say, right, for each of those years, with each of those months, what is the predicted minimum temperature? And then we can put them together. So we put the model predictions and the standard errors around those predictions into the main data frame. And if we just have a quick look at what that looks like, for every year, there is month 6 with its prediction of the modeled values. So what's the minimum temperature and the standard error around that. And then in order to visualize that, we'll just use the lines command to plot. And notice now we're not using raw data, we're using the predictions to plot against year. So we now have our model line in the predictions. And then because we've got the standard errors, we can actually produce confidence intervals. And so this time what we're going to do is we're going to create our upper standard errors and add those as a dotted line, and the lower standard errors and produce those as a dotted line as well. And because we're looking at the difference between the difference between June and if we want to look at December, for example, then we can plot those points and use exactly the same set of instructions again. So this time we're going to plot them as blue. We'll create a sequence in exactly the same way. We'll use the modeled data to predict a new set of values for December. We will combine those two together, and then we can visualize it with a blue line. So that in essence is a GLM. That is a very standard, very basic sort of GLM, but it does give you the ability to look at multiple terms in relation to a particular Y variable. I'm just going to catch up with PowerPoint, and then I'm going to show you what about if there was an interaction between month and year. So what if we wanted these slopes to not always be the same? You know, we don't have the same relationship in every month with temperature. If we wanted those to be able to vary, then we'd need an interaction. So we always start with our sort of picture, but then, and this is really important, that sort of when people are doing statistics, many people kind of get so bogged down in the stats that they sort of forget the biology side of things. They forget that that's the reason that certainly biologists, ecologists, etc. are doing this. It means that, yeah, people lose track of that. And so what we need to make sure is we're reporting the biology first and then using the stats to back it up. So here we start with the broadest part of our hypotheses, which was, is minimum temperature affected by year and is it affected by month? And by using the overall model, the summary.lm, or as was mentioned earlier, the summary.glm, we can have the adjusted R squared showing that there is nearly 90% of our variation being explained by this model, and that p-value is very, very low. So there is a high statistical significance. So yes, the minimum temperature was significantly associated with both month and year. But then more specifically, minimum temperature was positively associated with year, because we could see from the coefficients table, this value was 0.02, and we have the standard error, and then we can report the other test statistics. Notice that we had the numerator and denominator degrees of freedom as well. And then also temperature varied significantly between months. And again, this is overarching, so we can report that. And we can then go on to report the contrasts and say specifically in 2000, for example, in June, it was 8.78 degrees warmer than the mean January temperature in the year 2000. So we don't have a huge amount of time, so I'm going to carry on with the idea of interactions. As I say, What if we didn't want to only see that same pattern across all the years? What about it actually if the relationship between year and minimum temperature was influenced by which month it was? Then what we need is a two-way interaction. So what we do here is we add it in with a colon in between. Notice we have the fixed effects, the main effects that we had earlier, month and year, and now we also have month colon year as our interaction. And so what we'll do is we'll go into R and model that in a second, and then we'll have a look at the model validation. So with interaction terms, we have year and month now, and we've got month colon year, and you can have it month colon year or year colon month. So if we ran that model, notice now that as well as year, and obviously we're still missing month 6 because that's our default level, we now also have the relationship between month 1 and year. So this is now what is the relationship between year and minimum temperature when you specifically have January, the months of January. And so what we're seeing here is there is a positive influence in that relationship. So it is steeper in January than it is in some of the other months. But importantly, not significantly so. So actually, we're not seeing any interaction between month and year, except for in December, when you're comparing it with June. So the relationship between year and temperature, minimum temperature, is only significantly different between June and December. The other months, the relationship isn't significantly different in its slope compared with June. And as I say, as we plot these, that means we can see then, we can see what this relationship looks like with the plot, and hopefully the numbers then will make much more sense when we see the plots. So we've got our AIC. So we can compare this with our previous model, because although we have an interaction, everything else about the model is the same. So we had 1,445 before, and we've still got 1,445. So these models are very, very sort of similar in their efficiency. And if we look at the model validation side of things, we can see that actually we've still got this equal band of points. And so that's really good. And we've got those red lines going through 0. If we have a look at the QQ plot, so looking for the normal distribution of points, again, the vast majority, in the middle at least, are on the dotted line. However, they're very much tailing away on the left-hand side as well. So again, I would make sure that I didn't try and extrapolate beyond sort of the normal range of the data. Again, the scale location, we've got this slight downward trend, but actually we've got a good spread of data points across the full spectrum. And the Cook's distance, it is now more spread. However, we still don't see the Cook's distance anywhere on the outside, and therefore there are no unduly influential observations in this model. So as far as a model goes, it's absolutely valid. So the assumptions have been met, but the question is it the best and most efficient model that it could be? And so again, we're going to go on to drop model 1, and the test equals F. And here I was saying that, or earlier on I was saying that we always look at the highest order interaction first. So here, the interaction that we have is year and month. And what we're being shown is what the influence of removing that interaction would be. So if we remove year and month, our model would be significantly different. Now, this says that the AIC would actually go down, but what this star is saying is that there is a significant influence of this interactive term in the model. And so therefore, we keep the interaction in. If it wasn't important and we removed that and we did the drop one again, we would see year and month separately being shown in that table, because then we would be allowed to remove them. But we can't remove year on its own or month on its own at the moment, because the influence of the year-month interaction is significant. And so even though we only have the relationship between June and December being different, that is enough that actually this is an important term in the model. If we look at the summary.lm, we can then see that we've got 89% of the data sort of being explained. So we haven't actually gained that much at all from having this model in, but we are still explaining a significant proportion of the original data. Someone was asking about the equation that you'd want. So model one, asking for the object itself. I don't like the way that this is framed and formatted, but it does give you sort of what you've asked for. So it gives you the intercept. So in the equation that sort of you may have learned at school, y equals mx plus c, the straight line relationship. The plus c is the intercept, so that's the minus 53. And then the mx, the m is the slope, and so that m would be 0.03 of the x variable year. So you would be able to create your own regression equation from these data, depending on what the question was that you were trying to do. So if we then wanted to visualize that model, given the fact that we still have this interaction, we would then have a look at plotting our points and create the predictions. Again, note, I have used model one again, so I've overwritten the original model with this interaction term model. And so do be careful if you're going to do this, that you know which model you're using. If I create the new predictions using the bread frame and I add on the lines, this is again ones for June. Then if I add on my standard errors and I can plot the December one, we can see that because this is using the interaction term, this relationship between June and December is very different. And so this is kind of why it's important to add the interactions when it happens, because we can see that actually using the original pattern where we had the same slope, which was an average across all of the months, actually isn't truly reflective of how these data are going. And so we can see that actually the minimum temperature is decreasing in December, and this makes complete sense given the snow that we've had, especially in 2018 and 2012, etc. So this is, yeah, this pattern of colder winters, warmer summers, and just more extreme weather generally is what we're seeing across the data. So if I just go back and catch up in PowerPoint, we can see that, again, using model refinement, we need to go from the starting model to the final model, and we're going to remove non-significant terms one by one, starting with the highest order interaction. In theory, you can do any number of interactions you like. So if you had 5 X variables in the model, you could interact every single one of them. However, I really wouldn't advise that, because there are 2 things about that. One, you use up a huge number of degrees of freedom. Every time you put an interaction, you have to have enough data points to be able to, for the model to be able to calculate what the effect of that is. If you use 5 terms in interactions, and you have a 5-way term, then you're going to have very specific sort of questions effectively, and you need a huge quantity of data to be able to do that. As I say, the other thing is you then need to be able to explain it, and that is a real challenge. If you try and explain how the relationship between year and temperature is influenced by month, it's not too difficult. If, however, you try to then explain it by 3 other terms as well, it becomes much more complicated. And in the words of Alan Zier, who is a phenomenal statistician, you enter a world of pain. And that's a direct quote from one of his books. So yeah, start with the highest order interaction, but make sure that you don't have more than three sort of a 3-way interaction is more than sufficient for most data sets. That's what we've said, remove the highest order first, and then continue to remove terms only until only significant terms remain. So that's that's how you go about it. So that very much ties in with a question that's just been asked. So is there ever a case where you would not do a stepwise deletion for a GLM with 2 or more explanatory variables? So there are lots of ways of doing model refinement. Stepwise deletion is one of them. Model averaging is another one. We don't have time today to go on to that, but that is in the 5-day course, where you look at sort of all the permutations that it could be, and you take an average of those. Other ways of doing it is saying, well, these terms are part of my methods, and therefore I don't want to remove them. So for example, if I did this in 3 locations, so I took these temperatures, but rather than doing them across all of Wales, I specifically did them in 3 locations, I might want to say, well, my question is there a difference between these locations? Therefore, even if the locations weren't significant, I might include them to be able to report specifically that they weren't different. And I'd be able to report the impact of year and month on temperature was controlling for the fact that there was a difference in location. So yes, there can be times when that's when you wouldn't want to remove things. Other than that, if you're going to use the sort of AIC method side of things, then that's what you'd need to do. You'd need to kind of refine until you have the significant terms. And as we've said, that uses the drop model 1. At the end of all of this, once you've refined your model, once you've played about with the interactions and everything else, always go back and check your model assumptions, because at the end of the day, if you don't have a valid model, then it's not appropriate to report the results of those anyway. And as always, we have the sort of reporting of the coefficients, which you get from the summary model 1 or the summary.lm. And make sure that you know that the coefficient is for the first level. So make sure that if you're working with months, for example, and they're coded 1 to 12, that you know that the default is going to be 1. If you don't want it to be, you can change it. Apologies for the typo on the screen. We used to use this with a different data set, and the deframe $1 is just an error, so apologies for that. And then once you've run all of that, you'll want to rerun the model and have a look at your summary output. We've covered what the intercept is, but all of you guys have these PowerPoints and stuff, so you can kind of go back and look, and in case you need to kind of have a refresher sort of another time, then the intercept information is there. We've also got the positives and negatives coefficients, so the slope that you have with things such as year, variables such as year here, but also the difference in the means between categorical levels. And again, we've covered the drop one. So here, I've just added on an extra couple of sort of labels to it. You can and cannot if you want to, but plotting interactions is by far and away the easiest way of reporting the results. And then you can have the actual values from the coefficients table either in the appendix, or if you want to, you can report it in the table, but visually it makes sort of so much more sense to report it. So how would we actually sort of report these? Well, the same initial questions are the same. So minimum temperature was significantly associated with both in year. However, more specifically, the minimum temperature varied between months, but the relationship and the strength of these differences varied significantly with year. So which year it was influenced the relationship between month and minimum temperature, and that can be flipped on its head as well. And so the relationship between year and minimum temperature depended on which month it was. So within two-way interaction, you need to make sure that you're reporting what you want, but understanding that it works both ways. And again, we could go through and conduct a contrast, and we can have a look at these various differences. And again, you can see sort of how to report that at the bottom. And then, so this is reporting, but also interpreting, making sure that you're understanding that if you're using a contrast, you can look at the differences between June and December in particular given years. And so just to round up sort of all of that graphically, when the slopes are identical, it's because there isn't an interaction in the data set, or in the model, sorry. And when there are differences, it's because there is an interaction, and that interaction is significant. So that's the sort of really important distinction with GLMs and how you go about doing that. So what we could do in the end of the script, there are those contrasts that you've just seen, but also we've suggested that maybe you want to try and do some other contrasts of your own and have a play with the data and see what it's like if you remove one of the interaction terms, if you remove one of the terms, and then start doing, you can do some contrasts on lots of different levels. We're very nearly out of time. So the only other thing I wanted to do is I just wanted to say that if you have found this useful, if you do want to know more about all of these models, then we have this 5-day session in the 16th of May. And as I say, runs for 5 days. We cover an introduction to R. So if this has been a little bit much, we have an introduction session. We then cover 3 days where we cover general linear models exactly as is. We have generalized linear models. So we do count data, and we do binomial data with proportions and proper binomial data. We then move on to general linear mixed modeling, and particularly looking at the idea of how else to do these model refinements. So dredging and sort of other ways. We also then have general additive mixed models, and general additive models. We look at multivariate and spatial statistics as well. And the idea behind all of that is that we also have workshop sessions every morning and afternoon so that you have time to work on your own data with a suite of instructors. So there's myself and a few of my colleagues, and we then provide that time to you guys. So if you have any questions, then my email address is jez@ecoexplore.co.uk, which I will put in the chat. And if you have enjoyed it, then I'm absolutely delighted by that, genuinely. And also the other thing to say is, if you want to buy a guidebook, we fund all of our conservation through the money that we make from these courses and selling the guidebooks. We have a woodland in Wales, which we monitor and we manage for sort of declining species. And so that's where all of this money has come from. So thank you very much for your time, everyone. And yeah, any questions, I'll hang on for a few minutes. But other than that, thank you very much for your time. And I hope you have a good evening, morning, night, depending on where you are. Thanks very much.